Hi, it's a pleasure to have the opportunity to give you a presentation today, and I'm really sorry that I actually can't give you this presentation live. I'll be there at the end of the talk, though. I'll be able to join you for about the last 10 minutes of my allotted time. So hopefully if you can hold questions until the end, I'll be right back. I want to acknowledge today my co-authors on the work I'm going to present. So I'm going to present a paper that we've already finished, where the authors are Ionica Kilisser Lauder, Lorenzo Garcia Mazier, and Menza-Teanu. And we also have a paper that we're currently working on, which will have the same co-authors except Micah, who's left academia since. I want to also acknowledge the support of Women in Numbers Europe. That's where our community collaboration started. The support of the NSF, the National Science Foundations in the United States, that supports my research, and the French American Cultural Exchange Foundation, which has also supported this work. All right. So, the title is to compute modular invariants from period matrices, and I will tell you what that means. So let's start with some definitions. First, we will consider the Siegel upper half space. It's the space of all G by G matrices. So we pick a positive integer G, and we take all the G by G matrices with complex entries. These matrices have to be symmetric. So Z is equal to its transpose. And the imaginary part is positive, by which I mean, if you take the imaginary part of each entry in the matrix and compute the determinant of that, that should be a positive number. Okay, so you take all the matrices of that kind, okay, that are symmetric and have positive imaginary part, and you call the set of these the Siegel upper half space. We'll see that why is it called that, right? It's kind of weird, upper half space, oddly specific. When G is equal to 1, right, then you have a 1 by 1 matrix, which is just a complex number. It's automatically symmetric and then with positive imaginary part. So that's exactly the upper half of the complex plane. So this is a generalization of that. The elements of the upper half space are the period matrices. So the matrices that contain periods. Sometimes these are called small period matrices, and some people will reserve period matrix for G by 2G matrices, but here we're not going to deal with that. And why do I care about these matrices, as fun as they look, is because each of these matrices can be associated to a principally polarized abelian variety. And the goal here, right, is starting with one of these period matrices, which will have an approximation of, right? So a complex number, maybe think of pi 3.14, 159, so when you deal with a real number, most of the time you actually deal with an approximation of the real number, because real numbers are long and require kind of infinite information to really be known, right? So what we want to start with is an approximation of such a matrix. So a matrix with, approximate entries, like, the first digits of some complex numbers. And what we want to get out of this is an exact model for some associated variety. So I'm saying some associated variety. It actually won't be the abelian variety. It'll be an associated curve. The abelian variety will be a Jacobian. But the point that I want to make in this slide is that we want this model to be exact. So the model will be over a number field. And what we want are the exact values of these numbers, like root 2, not like 1.1, whatever, right? So we want to go from some floating point approximations to some exact numbers. It's kind of the crux of the problem. So here is a proposed program to do this. First is to define some modular invariants of the variety that you want to compute. So an invariant of the variety, right? Like, so something that belongs to the variety, but modular, by that I mean that the domain, right, the input that these invariants take, I'll want those to be period matrices because that's what I'm starting with. We want a way to get exact values for this invariant. So the rounding will happen there in that middle step. And then finally, a construction algorithm from the invariants to the variety that we want, right? Because remember, we want a model for some variety. So this is at once oddly specific and vague. So let me give you an example so that I can be very precise about what I have in mind. So let's get back to the G is equal to 1 case, the dimension 1 case. So like I talked about in that case, right, the Siegel upper half space is just the complex upper half plane. And so the, goal you might have in mind in this setting, right? The story in this setting would be starting with some number in the upper half space that corresponds to a CM elliptic curve. Okay, we have the CM theory allows us to do that, to just start with a number in the upper half space that we know will correspond to a CM elliptic curve. And from that, right, get a model for the elliptic curve, like some value for A and B, such that this is an equation for the elliptic curve. And here we'll want A and B to be exact, right? So if this elliptic curve is over the rationals, then I would want to know, like, this is 1/3, not 0.33333, okay? Or if this is over if this is over some number field, then you would want like exact values for the coefficients. So how could you do that, right? Well, the step one, finding your modular invariants for elliptic curves, kind of the invariant is the J invariant. And thinking of it as a modular invariant, right, which would be, don't plug like A and B, right, the coefficients of the elliptic curve to get the J invariant, but instead start with the period matrix. So like the tau in the upper half space. So we do have an expansion, a Q series expansion for the J invariant that can allow us, right? So if we like Q be 2 pi I Z, where Z is that number, then the number in the upper half space that we started with, then you can compute this to as many, digits of precision as you want and get an arbitrarily good approximation of the J invariant of your elliptic curve. Now, how are you going to go from the approximation of the J invariant to the actual J invariant, right? The kind of rounding step happens with the invariant. Well, here we'll use that. We know that the J invariant of a CM elliptic curve is an algebraic integer. So here is a way to leverage that information. Okay, so you can compute a full Galois orbit of that J invariant. That's, again, thanks to CM theory. We know that. Suppose the elliptic curve that had CM, right? Because all along that you're trying to compute the model of an elliptic curve with CM. And suppose you know that this elliptic curve has CM by the ring of integers in an imaginary quadratic field. Okay, some field K, and this elliptic curve has endomorphism ring OK. Then you know that the Galois conjugates of the J invariant of this elliptic curve are actually the J invariants of all the other elliptic curves that have CM by that same ring of integers. Okay, here I put a ring of integers for simplicity, but I could have put any order in an imaginary quadratic field, and this would still be true. We know the connection between the Galois orbit of the J invariant and the elliptic curves whose J invariant those are. They all have the same endomorphism ring. So here, right, since you know how to compute a period matrix for one elliptic curve with CM by OK, you can just get a period matrix for each of them, right? And then compute the J invariant for each of them to as much precision as you want. And then form this polynomial, right? X minus the first J value, X minus the second one, multiply them all together, and you'll get some polynomial which has integer coefficients. Okay, because these J invariants are algebraic integers, their minimal polynomial is the monic minimal polynomial has integer coefficients. So if you've computed all these J invariants to enough precision, when you multiply or add and add all the things, right? You can rig it in advance so that you know that the answer you'll get is within 0.5 of the correct answer, right? You can compute how your error propagates in the computation. And then if you know that you're within 0.5 of the correct answer, and you know the correct answer is an integer, then when you see the number, 10.612, you know that that's actually 11, because you're rounding to an integer. Okay, so that's why we kind of go through this, like computing an invariant and then rounding and then getting a model, is because a lot of the time with the invariants we have these kinds of results. So here, using that it's an algebraic integer. So then once you have an exact minimal polynomial, the J invariants are roots of this minimal polynomial, and from the J invariant you can reconstruct the elliptic curve that you need. So that's to give you an idea of what I have in mind here. Now, this is about SIMMAC elliptic curves, so you might wonder how to generalize this. One direction of generalization is to generalize to CM abelian varieties. The purpose of this project, the reason why we were interested in this is for cryptography. And in that case, abelian varieties are a little bit too complicated still to serve in computations. So we'll want not only a CM abelian variety, but a CM Jacobian. Okay, and then we'll want to compute the associated curve. Why is that? Because to compute on the Jacobian, I don't actually need an equation for the Jacobian. If I have an equation for the curve, I can do all of my Jacobian arithmetic with the points of the curve, and the curve has a much simpler equation. So in higher dimension, instead of dealing with an elliptic curve as the Jacobian and then the same elliptic curve as the curve, in higher dimension we have a Jacobian and a curve, and they're different. And though the Jacobian has good reduction everywhere, the curve doesn't, right? So in dimension 1, when they're the same thing, the CM of the abelian variety gives the curve good reduction everywhere, which ensures that the J invariant is integral, right? Is an algebraic integer. In our case, when we go to higher dimensions and we're computing invariants of curves, then those invariants can have denominators, right? They won't necessarily be algebraic integers, even though the CM theory still applies and tells me that the Jacobian has good reduction everywhere. So when we compute invariants of the curve, the class polynomial that we'll get, right, this analog of doing like x minus the invariant and multiplying them over some Galois orbit, this class polynomial will have denominators in there. And because the rational numbers are dense in R, the rounding trick that we use for the integers won't work. So that's our problem. Okay, so just to be more precise, in this talk, I'll be focusing on the G is equal to 3 case, which means that my CM field will be a CX CM field, so twice the dimension of the variety. So fix K, a sextic CM field, and J some modular invariants, right? So some modular form that I can evaluate on some period matrix that belongs to an abelian variety. Then once again, by CM theory, if I loop over all the abelian varieties that have CM by the same, in this case, I once again chose the ring of integers in K, then I will get a polynomial with coefficients in Q, but I can't ensure that they're in Z, because these denominators might not be these invariants might not be algebraic integers. So what I want, right, is some small, so in this case, the smallest positive integer, such that when I multiply the whole polynomial, this is the same polynomial, but now multiplied by some integer d to clear all the denominators, right? I'm going to call this integer the denominator of the polynomial. And what I'm looking for is this denominator or a small multiple of it. Then this will allow me to apply my dimension 1 technique you know, exactly, right? Because if I know this number D in advance and I multiply through, then I'll be able to round the numbers because they'll be integers. So note here, right, that I can't compute this polynomial and then look at the denominators. What I need to know is the denominators in advance, like this D in advance, so that I can clear and then round to see the integers that would have been the numerators, right? So we need a technique to know a priori what denominators can appear in this polynomial. So going back to my situation, right, like I talked about, what I will want is a Jacobian of a curve of genus 3, which is an abelian variety of dimension 3. Why a Jacobian of a curve? For computations on the curve, right, so that I can do my arithmetic on my abelian variety easily. Why simple? That's a computational artifact. So the way that I have to generate period matrices is to start with a CM field like K, right, the sextic CM field, and or actually like the order in that sextic field, and then create period matrices of varieties that have CM by that order. And if that abelian variety is simple, right, and that's something that I can control, CM theory gives me control over that, then I know that it's a Jacobian, right? So I don't start out knowing it's a Jacobian, but I have a simple principally polarizable abelian variety, which I know is a Jacobian. So that's kind of part of, earlier work, except this for now, I have a curve of genus 3. It has a simple Jacobian. I know that, and I know that the order, some order in a sextic field embeds in the endomorphism ring of Jacobian, so it's a CM Jacobian. And throughout, I'm going to define some number field M. So I forgot to write that, right? But not just any field in C, but one of finite degree over Q, such that the Jacobian is defined over M and has good reduction everywhere, and C has a stable model. So that's another thing that's guaranteed to me from CM theory, that I can get that. Okay, that's just to ensure everything works. So our first result in earlier work that's now published is that if C, right, your genus 3 curve happens to be hyperelliptic, then under some really mild conditions, if you have a modular invariant of the curve and an odd prime such that P divides the denominator of that invariant, then C has bad reduction at that prime. And I'll tie this into the problem later when I have more support, okay? But for this slide, let me just give as a comment, right, the mild conditions are just, well, you don't want to pick a modular invariant that's like already has a denominator. Like the J invariant that I presented before for elliptic curves, right, is integral, is an algebraic integer for CM curves. But if I took the same value, J over 2, right, then every time the denominator would have a 2, but that's kind of artificial, right? So like what I mean is there is a notion of like an integral invariant, and that's what I mean. I want like some kind of integral invariant that doesn't have denominators kind of for trivial reasons, so that when P divides the denominator, basically it has to come from bad reduction of the curve. Okay, and so in that case, that implies that the prime below this P in M divides the denominator of the class polynomial. So this earlier work of ours tells us which primes divide the denominator. So now the next question, right, is what's the power of the prime that divides the denominator? Note in my theorem that it was a hyperelliptic curve, not a plane quartic, right? So there's two kinds geometrically of curves of genus 3, hyperelliptic and plane quartic. Why doesn't our theorem apply to plane quartics? Is that plane quartics have another kind of reduction, hyperelliptic reduction, right? So when I have a hyperelliptic curve in characteristic 0, and I reduce it mod P, it'll either remain hyperelliptic, good reduction, or have bad reduction. When I have a plane quartic curve in characteristic 0 and I reduce it mod p, maybe it'll remain in plane quartic, which is good. Maybe it'll be a hyperelliptic curve, which is good reduction, but of a different kind, right? Or it'll have bad reduction. So in our technique, we use the fact that not hyperelliptic reduction is automatically bad reduction. This doesn't apply for plane quartics, where not having plane quartic reduction doesn't automatically mean that you have bad reduction. There's this other case in the middle, which is good hyperelliptic reduction. And that is an obstacle to apply our result. That's why we can't do that. Okay, so we would be in a situation, to say it differently, right, where P can divide the denominator of the invariant without being a prime of bad reduction of the curve. And for us, that's an obstacle. We need that when P divides the denominator of the modular invariant, it's a prime of bad reduction of the curve. And I'll talk about that again in a second. Oh, actually, I'll talk about it right now. Sorry, I thought it was on another slide. But in that case, right, when you have hyperelliptic reduction, the Jacobian, the reduction of the Jacobian can still be simple instead of being decomposable. Okay, and so what we'll be using is that in the hyperelliptic case, automatically when P divides the denominator of the invariant, it's a prime of bad reduction, and the Jacobian is not simple mod P. Okay, so let's see how that works, right? So suppose that I have a prime and C has bad reduction, right? So let's specifically talk about the bad reduction case here. That's the one that we get automatically as soon as the prime divides a modular invariant in the hyperelliptic case. Then, right, the curve, when I reduce it mod P, so I'm still in the genus 3 situation, right? So my curve, when I reduce it mod P, will have still a Jacobian, right? And the Jacobian will either be a product of 3 elliptic curves or a product of 1 elliptic curve and a Jacobian of a curve of genus 2. Okay, so that's when a curve has bad reduction, which is a situation I can put myself in the hyperelliptic case. And then what I use, in fact, is like a little bit more than that, right? Because this is like 2 cases, is Chai, Conrad, Oort show that actually, if what I get, right, so I start with a curve that has bad reduction, that means its Jacobian is decomposable, right? I can break it up into Jacobians of lower, abelian varieties of lower dimension. And then Chai, Conrad, Oort actually says that whenever that happens, my reduced abelian variety is isogenous to 3 copies of the same elliptic curve. Okay, so whenever my curve C has bad reduction, then I know that the Jacobian mod P is isogenous to 3 copies of the same elliptic curve. So it means that the endomorphism ring of the Jacobian mod P is isomorphic to 3x3 matrices with entries in some quaternion algebra, right? Because that's the endomorphism ring of E, and then a product of 3 elliptic curves has endomorphism ring the 3x3 matrices over that endomorphism ring. Okay, so in particular, we get an embedding of the endomorphism ring of the reduced variety into 3x3 matrices with entries in a quaternion algebra. And then, right, how do I use that? I get that the endomorphism ring in characteristic 0 embeds in the endomorphism ring in characteristic P. So let's recap, right? Thanks to our earlier work, when we have a hyperelliptic curve of genus 3 and a prime divides the denominator of the class polynomial, right? So a prime divides a denominator of an invariant, then we get bad reduction of the curve, modulo that prime. That tells us that the Jacobian mod P is decomposable. That tells us that the Jacobian mod P is actually isogenous to 3 copies of an elliptic curve, which then tells us about the endomorphism ring of the reduction of this Jacobian, right? So like all kinds of stuff happens. So whenever P divides the denominator of the class polynomial, we have an embedding of the endomorphism ring of the Jacobian of the curve into this 3x3 matrices over a quaternion algebra. And as it turns out, that's very special, and that allows us to say some things about the whole situation. Right? So let me just recap now with a little bit more visual support, right? So whenever an odd prime P divides the denominator of an invariant, through that chain of event, you know, like looking in the Jacobian, the reduction, blah, 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 we get some embedding of the ring of endomorphisms of the Jacobian in characteristic 0 into some matrix algebra. And as it turns out, that's very special. Not every order in a sextic CM field can embed into this specific algebra, right? Like the existence of this embedding puts some conditions on P. And so that's how, right? That's one way we can get to identify the primes that can divide the denominator. Now, from previous work on this in dimension 2, we have reason to believe that actually the exponent to which P divides the denominator of the polynomial, right? So I talked about how the primes of bad reduction give us like what primes divide that denominator that we're trying to compute, but we don't need like just the primes, we need also, you know, the exponents. So we have actually guided from earlier work of Gorin-Lauter and Lauter-Varai that the number of embeddings, right, the number of ways in which we can put this order into this matrix algebra should give us some information about the degree of the prime. Because roughly speaking, each different embedding should come from a different curve, right, that has bad reduction, right? So it should come from a different curve that has P dividing the denominator of its invariant. And so that should tell us like how many times essentially P divides the denominator of the invariant. Okay, so our new work is to try to tease out this connection a little better, our forthcoming work. And why, you know, do I have this like weird symbol, right? Why is it not just equal? Well, it's clear that it's less than or equal to. Okay, so like each embedding could correspond to a different curve with, you know, bad reduction at P. So you know, but the thing is that there might be too many embeddings, right? So the thing is that the same, you know, reduction problem, the same curve with bad reduction, could appear in our embedding problem in many ways. Okay, so to improve the bound, right, we might want to consider like when are two embeddings here essentially corresponding to the same problem to start with, right? The same curve with the same Jacobian that has bad reduction mod P. If we understood that, right, we could cut down like from, you know, the same curve creating many different embeddings. And then another issue that happens in dimension 3, right, is that actually some of these embeddings are going to come from non-simple Jacobians in characteristic 0, which we don't want to count. Okay, so we started at the beginning at some point, I said, okay, let's see be a curve of genus 3 with simple Jacobian in characteristic 0. So we want to be able to ignore the Jacobians in characteristic 0 that are already decomposable, because then their reduction will certainly be decomposable, and so they'll create more embeddings there, but that don't correspond to our starting problem that we're trying to solve. So those two issues. So we do say some about the isomorphisms in our forthcoming paper. But this issue with the non-primitive embeddings, we have some partial results, how to ensure, you know, that the embedding comes from something non-primitive, but that's still very much something that we need to do more work on in the future. All right, so I should have joined the meeting by now, so hopefully I'm there, and thank you for your attention.